So friends, in trend analysis, what happened was we wrote something like this. Y is equal to B0 plus B1 multiplied by T plus some error, right? So Y was a function of time period. This was a trend model, friends. So what is an auto-regressive model, friends? Basically, it is nothing but the current value yt is a value derived from one of its previous values. So let's say it is derived from its immediate previous value. So how the equation will be? Yt is equal to b0 plus b1 into yt minus 1. That is the value of y at just the previous period. Plus obviously some error. So in this equation, yt, that is the y at current time, let's say t is equal to t, is a value which is a function of its previous value, previous period's value, yt minus 1. This is an auto-regressive model, and more specifically, an auto-regressive model of order 1, AR1. Why 1, friends? Because y is derived from its immediate previous value. So yt is a function of yt minus 1. That is why it is called a AR1. So this is a first order autoregressive model, right? Now what is the second order autoregressive model, friends? This is given by something like this. Yt is equal to b0 plus b1 yt minus 1 plus b2 yt minus 2 plus error. Let's call this error 1, error 2. Okay. This is called the second order autoregressive model, or AR2. Now we can generalize this. Yt is equal to b0, b1 yt minus 1, b2 yt minus 2, bp yt minus p, plus some error. This is called a pth order autoregressive model. Now friends, for an autoregression model to be valid, it has to be covariance stationary. Now what do we mean by covariance stationary? Basically 3 conditions if fulfilled, the autoregressive model can be called covariance stationary. What are those 3 conditions? Number 1, the expected value of whatever we are measuring, let's say expected value of x or y, has to be constant, k, where k is a constant. Right? Across time periods, if this k keeps on changing a lot, then this cannot be called covariance stationary. Number 2 is covariance. The covariance of this variable at a certain lag, let's say xt minus s, the covariance between these two has to be constant. Let's give this a value called mu, where mu is a constant. Again, if this mu value changes with respect to time zones, then we cannot call the AR model, autoregressive model, to be a covariance stationary model. The third point, the mean value of x has to be constant. Let's give it value lambda, where lambda is constant. So the mean has to be constant, the covariance has to be constant, the expected value of x also has to be constant. Now the third point is the variance of x has to be constant across time zones. Variance of x has to be constant. So the variance of x has to be constant across time, covariance has to be constant across time at a certain lag, and the expected value of the variable also has to be constant across time zones. These 3 if simultaneously available, then only we can say that the autoregressive model is covariance stationary, right? If any of these do not satisfy, then what will happen? Then the slope will become biased. The B1 will become biased. And the output estimates will become spurious or unreliable, right? So we will say that the AR has become invalid. And we will be not able to do any hypothesis tests. So this is going to be the consequence if the covariance stationarity condition is not fulfilled by an autoregressive model. Now, how do we test for an autoregressive model covariance stationarity? Unfortunately, Durbin-Watson model is not valid for autoregressive models. So how do we do that? We do that through autocorrelation tests of errors. Let's see how we do that. So friends, let's say we are testing for serial correlation or autocorrelation at a lag of t minus s, right? So t with respect to t minus s we are trying to test. How do we test that? So let's say we are trying to measure the serial correlation of an autoregressive model at lag of s time periods. So we are comparing the variable at t with respect to the variable value at t minus s and trying to understand whether serial correlation exists or not. So how do we do that? So first we estimate the value of the variable x at time t minus s. Xt minus s is equal to, let's say, b0 b1 x t minus s minus 1 plus b2 x t minus s minus 2. This equation lag till s periods, right? So b s x t minus 2s plus the error for the variable x t minus s. So this is the first equation that we develop. The second equation is we try to estimate the value of xt. Xt is equal to b0 plus b1 xt minus 1 plus b2 x t minus 2 plus bs x t minus s plus error for the variable equation of xt. Now we have these two error values, friends. Error t minus s, error t. Now we do a correlation test for these two error values, friends. How do we do that? Correlation t minus s is equal to expected values of error t minus s minus expected value of error. Now in a time series, the expected value of error is 0. This expression multiplied by error for t minus expected value of error, which is again 0. This entire thing divided by the variance of the error value. Variance means standard deviation square, right? So here we have written here in place of variance we have written phi, right? Let me change the value here. Let me change the symbol here. It is basically sigma square. Now we are good, friends. So this is the correlation value, friends. Now how do we decide whether autocorrelation exists or not? What we do is, let's say there are 100 time periods in the model, right? There are 100 time periods. What we do is, we divide this correlation by root over of 100 and check the value of this. So if this value is more or less equal to 0, that means there is no serial correlation or autocorrelation. So in general terms, let's say if there are t time periods, capital T time periods, then we divide this correlation value sigma t minus s rho t minus s by root over of capital T. And if it is more or less equal to 0 or nearby 0, that means there is no serial correlation or autocorrelation at lag of s, at the order of s. So this is the litmus test, friends. The value has to be nearby 0 or exactly equal to 0 or nearby 0 for there to be no autocorrelation or serial correlation. Now friends, the obvious question that arises is, how much different from 0? So what value or how much different value from 0 is different enough for us to consider that whether serial correlation exists or not, right? So let's say there is a model which has 4 lags. That is a 4th order autoregressive model. So xt is equal to b0, b1 xt minus 1, b2 xt minus 2, b3 x3 t minus 3, and b4 xt minus 4. So we are using 4 lag variables to describe the variable itself. Okay, so we write it t minus 4, the error also. Now, when we measure, let's say when we measure the autocorrelation or the correlation at t minus 1 divided by, let's say the number of observations is 200. So we keep it root over of 200. This value comes to be 0.57. Similarly, for t minus 2 root over of 200, this value comes to be 0.25. Similarly, for the other two variables, it comes to be 0.7 and 1.1, right? 1.1. So these are the values, right? Now, how do you know which? These are all very near to 0, right? These are all sufficiently near to 0. So how do we know which correlation is valid and which one is invalid? That is, which one does not have autocorrelation or serial correlation and which one has autocorrelation or serial correlation? We have a way to do that, friends. Here there are 5 parameters: b0, b1, b2, b3, b4. There are 5 parameters and the number of observations is 200. So we do one thing, we try to find out the t statistic for 5 parameters and 200 observations. Let's say the critical value of t is 0.98. So I have not calculated the exact value, friends. This is just I am using it for this example. This may not be the correct value of t in actual t tables, but I am just taking it as a value so that we can understand this example. Okay. So let's say the value, critical value is 0.98, right? Now compare this critical value with these values, friends. These 4 values. So this one is less, so this is good to go. So at t minus 1 there is no autocorrelation. At t minus 2 also there is no autocorrelation because this is less than the critical value 0.25. At t minus 3 also there is no autocorrelation. Only at t minus 4 we have the value greater than the critical value. So this one has an autocorrelation. There is autocorrelation or serial correlation here, right? At t minus 4. So the rest of the 3 observations are good to go, but the last observation, obviously at t minus 4 lag we are finding some autocorrelation. So the model at t minus 4 order is invalid. Okay. So what we have done is we have just compared the critical value with the value that is being calculated and try to understand whether the value is exceeding the critical value or not. If the value is not exceeding the critical value, obviously there is no autocorrelation. If it is exceeding the critical value, there is autocorrelation. It's as simple as that, friends. Now, friends, we will understand how the performance of an autoregressive model is measured. So, friends, there is something called root mean squared error or RMSE, which we use as a metric for performance for autoregressive models. So, let's say For the same kind of evaluation, we are using a AR1 model and a AR2 model. That is a second order autoregressive model and a first order autoregressive model. And this one, the AR1 model gives a RMSE of 1.25 and the AR2 model gives an RMSE of 1.7. So the root mean squared of the error is more in case of the AR2 model. So performance is better in case of AR1 model. This is a less error, right? Error less means performance is more. So we select AR1 instead of AR2. Now friends, we will look at one more property of autoregressive models, which is called mean reversion. So mean reversion basically means, let's take the example of a stock price. For example, let's say the price was moving like this and some fundamental changes happened and the values now are expected to move like this. So till this point it was growing, and from this point onwards it's expected to not grow, and not only not grow, it's expected to degrow. So this is the price of the stock, the vertical axis, and this is the time. So if we consider this to be an AR1 model, how do we represent this, friends? This point, let's call it the point M, or the point of mean reversion. So how do we predict at what point this mean reversion will occur, friends? Logically speaking, at whatever point this happens, the phenomenon that happens at point M is basically this. PT becomes equal to PT plus 1. First the values become equal, right? Because there is a flattening of the value here. Here there is a flattening happening. So if the flattening is happening at this point, PT is equal to PT minus 1 at point M, right? So from this equation we can predict at what value the mean reversion might occur for this time series, right? So PT is equal to, we have said this is an AR1 model, so this is going to be B0 plus B1 PT. If we rearrange this, PT is equal to B0 by 1 minus P1. So at this level, the mean reversion is predicted to happen for an AR1 time series model. We can generalize this for any variable xt of AR1 model. The mean reversion is predicted to be coming at P0 by 1 minus P1. Right, friends? So this is the value prediction. If somebody asks you that this is an AR1 model, the equation goes like this: xt is equal to B0 plus B1 xt minus 1. What is the value at which the mean reversion will happen? Tell us the value. Tell us the value. What you will do? You just rearrange this equation and replace xt minus 1 with xt and say that it will happen at xt is equal to B0 by 1 minus P1. Obviously B0 and B1 should be given. B0 and B1 should be given, and by measuring this you can predict the mean reversion point. It's as simple as that, friends. Instability of AR model parameters. Parameters means we are talking about B0, B1, B2, etc., etc. These coefficients and intercept. We are talking about the parameters. So why are the parameters unstable, friends? So specifically being a time series, what happens is many a times there are regime changes which influence the regression model itself. Let's say you're trying to plot the GDP numbers of USA with respect to last 50 years of time. So the vertical axis contains the GDP and the horizontal axis contains the years, that is the timelines, 70 to 80, 80 to 90, then 2000, 2010 and 20 onwards. Let's say the GDP numbers look something like this. Now friends, there is a problem in this data. This period of 70 to 80 was a period of great changes and high interest rates. There was complete decoupling from the gold standard, and the interest rates were soaring high in these periods, which is not at all similar to, let's say, period between 2000 to 2010. Here, the rates were very low, the interest rates were almost zero, and the fiat currency system had stabilized. There was a dot-com crash in 2000 which had brought about many economic changes. So these two periods are completely different, right? And again, these two periods were completely different from the period of 2010 to 20. Here, the quantitative easing was happening full-fledged without that much impact on growth. The banks have been reorganized, the regulations had been reorganized of the financial systems because of the financial crash of 2010. So all these fundamental factors were different. Now, it might so happen that if you try to draw a regression line, you will find that the errors are showing autocorrelation. These are not the exact GDP plots that I'm doing here. I'm just trying to take an example. Here you can see the errors are biased on the downside. And here the errors are biased on the upside. Especially 2000 to 2010, and then again some flattening is happening. I'm just guessing how it could be. But still it is upward biased in this entire regression. Now, this regression is having autocorrelations in the error part. Obviously, this is not a time series that we can bank on, right? So why this is happening, friends? Because there are different regimes being collated into one. Different regimes. That is a problem. Now let's say each of the years are taken as one period, right? And you draw a AR1 model, an AR2 model, a AR10 model, AR20 model, like that, right? And among them, you see that the AR10 model is faring the best in terms of root mean squared errors and also in terms of checking the autocorrelations. So we will choose this one over AR1 model, AR2 model or AR20 model. So this impacts the parameters, friends. How? Because we have chosen a timeline of 50 years, we are finding that the parameters of AR10 model are giving the best regression. On the other hand, if we, for example, say regress for 20 years, we might find that the AR2 is giving the best regression. Or if you regress for a period of 10 years, last 10 years, what is the situation? Then we might find that the AR1 model is doing much better. And the parameter values will change for each of them. So the parameter values will depend on the entire universe of the time zone that you are choosing. And this makes the parameters unstable. We define this as the instability of the parameters of the ARP models. Now friends, we'll look at a special case of autoregressive model which is called a random walk.